So in this video we're going to talk about convex mirrors. And I'm going to sort of bring back this concave versus convex picture from one of our earlier videos. We have to remember that these are curved mirrors. Think of them as spherical mirrors. If we had this big sphere and we cut a portion of it and we made the outside reflective, that would get us a convex mirror. Okay, so in a convex mirror, the mirror sort of bulges outwards towards the object. And so we can talk about properties of convex mirrors in the same way that we sort of talked about properties of concave mirrors. We still have C, the center of curvature, which would be the center of the hollow sphere from which this mirror was cut. We still have F, the focal point, which is halfway between the center of curvature and the mirror. And we can still have sort of our other, we have our principal axis, and we still have some of those other values. We have R, the radius of curvature. We have lowercase f, the focal length. All of those things. The thing to notice is that all of these, though, are on the back of the mirror, sort of behind the mirror, in comparison to the observer, which is makes this sort of more interesting. Again, another comparison. Last time we discussed that concave mirrors, they do follow the law of reflection. However, it doesn't look it if you just look at this ray, but notice that the normal line for anywhere on a concave mirror goes through the center of curvature, and that, of course, the incident and reflected rays angles are equal to each other. And if we think about this with a convex mirror, that still follows. If we extend the normal line behind the mirror, it would pass through the center of curvature, and that would be for any ray on the convex mirror. Now, what's interesting about concave versus convex mirrors is that concave mirrors are what we call convergent mirrors. So light rays converge. If we remember, we also could draw on this concave mirror a ray through the focal point that reflects parallel, and we get light rays that converge here. And so we have these light rays converging in front of the mirror, so this is called a convergent mirror. Convex mirrors, on the other hand, are considered divergent mirrors. If we think of another ray, right, or another ray, or another ray. Look at all these different reflected rays here. This one, this one, this one, and this one. They will not converge on this side of the mirror. They are diverging from each other. They will never meet on this side of the mirror. And it turns out they will only meet in terms of their lines of sight behind the mirror, very similar to a plane mirror. So these are considered divergent mirrors because the rays of light diverge from them. So some reflection rules. Unfortunately, this picture only shows one of the reflection rules, but you can imagine the opposite. The reflection rules are pretty similar to the ones for concave mirrors. Notice that incident rays parallel to the principal axis reflect in such a way that if you extend the ray behind the mirror, because remember, all of our sort of interesting values associated with mirrors are behind the mirror now, and the rays don't actually go there. So we have to extend things backwards. If we extend the reflected ray, it would go through the focal point. So the reflected ray does go through the focal point if you extend it backwards towards the focal point. So that's our first reflection rule. And you can imagine that pretty much these are opposites. So you could take this and say, well, what if this was the incident ray? And the incident ray, its extension passed through the focal point. So if the extension of the incident ray passes through the focal point, well, its reflected ray would be parallel to the principal axis. So very similar to our concave mirror rules. They just look a little bit different, and to make sure you get them right, you have to extend past. Again, remember, for both of these, the normals go through the center of curvature, or their extensions. go through the center of curvature.